you quickly try share your screen so
Yeah,
we can
will do.
start right at time?
So, okay, is that coming through?
Yes, we can see your screen, so you are all good to go. So you can start sharp at 1 p.m. Eastern time.
Awesome.
All right, thank you.
Okay, I'm showing 1 o'clock, so I'll just kick off. So I'm going to give you a rundown of a project which I've completed in my role as a data scientist at Ferguson to use some of the tools which Dave in the previous presentation was talking about to build out a neural net using TensorFlow to really deliver a very useful product in a very practical setting. And so what I'm hoping to do is give a very high-level overview of the task that we wanted to accomplish, and then get into the weeds a little bit with some of the details on how I actually built out the process and why I opted to use TensorFlow as my tool of choice. And yeah, I think we can have plenty of time for questions as well at the end and have a bit of a discussion about the best tools for this type of job. So without further ado, so just give you a little bit about my background of Ferguson, talk a little bit about the specific project and the problem that we needed to solve, and then I'll just go over some of the more technical details and finally wrap up with an overview of how we actually turn this into a real world solution, which helps the business team out with their product management. So I am currently the lead data scientist at Ferguson Enterprises. If I seem a little bit off my step today, it's because I just handed in my notice and accepted a position elsewhere. But this is currently my role. My background is in engineering, and now I specialize in machine learning. And this photo is from the last time that I spoke at Azure Data Fest, where in happier times we were all able to congregate and I'd be able to give the presentation in person. But great to be back talking to my laptop in any case. So a little bit about Ferguson. You may have some experience with the company or just, be aware of the company's existence. So we are the largest plumbing and lighting distributor in North America. So with all of our subsidiaries, I think we have over $20 billion of revenue, and then a very sprawling network of over 27,000 full-time associates, 1,400 locations that we sell products from, and quite a sprawling catalog of 3.5 million products that we sell. And this figure is probably a little bit out of date now, but as of the time of writing, there were 23% of our revenue was coming through online sales. And I'm sure we can all appreciate that there's probably been quite a dramatic shift towards e-commerce in recent times. So it brings us quite saliently onto the problem which we wanted to solve. So obviously with e-commerce being an increasingly important avenue of our business, we want to be able to maximize our ability to sell products through the website. One of the major challenges that Ferguson has had in this space is that because a lot of our data architecture was designed in the 1980s, we haven't, and modernizing is ongoing. A lot of our data quality is not where it needs to be to facilitate a lot of the processes that we would like to put forward. So the most obvious one being that of our millions and millions of products that we would like to be able to sell through the website, so 1.3 million web products which were tagged to be sold through the website as being appropriate for consumers. Only about 800,000 had the correct level of attribution, which would allow them to be put in the right folder on the website. It sounds like quite a trivial problem, but you might have a product which is obviously a tap, but unless we have in the web taxonomy attribute a label to say that this is a bathroom sink faucet, there's no way that we can locate it in the right place on the website and make it searchable and therefore be able to sell it. So we are in a situation where over a third of the products that we would have liked to sell through the website, we actually had no capability to do so because very simply we didn't know what those products were, even though they were in our product file. So obviously this was a problem that was already being solved, but the solution to solve it was to have human beings go through the product file, try to understand really garbled 30-character product descriptions with a load of abbreviations and acronyms and symbols and whatnot, and try and work out what type of product it was and manually assign it to the web taxonomy. And as you can imagine, that's a very slow and expensive process. So the brief was to see whether we could design a machine learning tool that would be able to ingest our product data and do some of that categorization in terms of either automatically assigning products to the hierarchy or at the very least generate a process that would increase the efficacy and speed of human beings who would ultimately do the assignment. So to give you a little bit of an idea what the overall ask was in terms of a machine learning piece, so we really just had two main attributes, which would be our vendor ID and our product description. And so you can see from looking at these first four products here, we can see that, obviously our elbows we want to have in the elbow section, and our pipes we want to assign to the copper pipe section of the web taxonomy. And so the idea is to see, can we build a machine learning model which can do essentially what is obvious, that we see a product with a word that looks a lot like elbow, and we probably want to assign that to be an elbow section. And then similarly, we have another product which looks like it should be a copper pipe, and can we assign that to the copper pipe section? So it's a task that is ideal for machine learning in that it can be done by a human being by looking at the data. But the real issue is the scope and the scale of the data. And so the challenge is to automate that process so that it can be scaled up to a larger production application. And obviously, you can imagine that when you have almost 2,000 different classes which you're trying to assign products into, your 500,000 products which you have outstanding, and then the addition of tens of thousands of new products being added to the catalog every month, there's no way that you can catch up to that without spending hundreds of thousands of dollars on outside consulting to get the manual work done, which was where we stood when we started this. So the basic overview of pre-processing the data before you can even start doing any machine learning work, and these are steps that you would really want to do in any sort of machine learning task. So obviously removing dead products and duplicate data points, mapping abbreviations. So we were very fortunate that we had a dictionary given to us by the business, which would enable you to compare. I don't have a good example of here, but you would have a random, like you might have SM for small. And so we had a dictionary which told us when those abbreviations would be used. But we also needed to do things like stemming words down to basic roots so that you could, for example, stem elbowing down to elbow so that the machine learning process would see those as the same word. And then a little bit of good practice for data science. So trying to remove or upsample some classes with very few SKUs where we don't have enough data. So to try and balance the data. And then obviously just things like cleaning special characters from text fields, all fairly straightforward stuff which you would want to do in any problem like this. So ultimately, where you want to go from a machine learning standpoint is where you start with some very either categorical fields or text fields. Ultimately, your machine learning data set should look like a big matrix full of ones and zeros. And so a lot of once you've done the initial pre-processing, which is to clean up your text fields, you need to do that transformation process, which gives you this binary matrix, which has just ones and zeros, which your machine learning network can ingest and do all of its clever arithmetic on. And so this is what you can see what it would look like. So for product 1, 2, 3, 4, we just have ones in our one hot encoded categorical field. So we can see that it's in plumbing warehouse as its vendor, and then it contains small, brass, and elbow in the product description. And so, and again, we have our target, which we're trying to predict into. So for the classified data, we have our target variables set there, whereas for our unclassified data, those are ultimately the values which we're trying to calculate and predict using our machine learning tool. Now, PiSpark, which is the tool which we used for most of our data pre-processing. So I should say that we did all of this work in Databricks. So Azure Databricks was our platform where we created out this data pipeline. And that has the advantage of being native to Spark and giving you the ability to use all of the tools which you have available in PiSpark to really speed up a lot of those data pre-processing steps. So particularly when you're in an environment like Ferguson, where you're dealing with an awful lot of data in terms of, millions of records of product files, and also when it comes to transactional data, hundreds of millions of records for invoices, where we need to be able to do a lot of analysis, which would be very challenging, if not impossible, to do in ordinary computer methods if you were just to use straight Python. So this is why we've been able to get a really big lift out of our ability to combine working with Python in some areas where we need to do local processing like machine learning, but then backing that up with the PiSpark Python API to really do some of the big data stuff where you need to do things like join very large data sets and do things like a lot of the cleaning of the product data. And so PiSpark ML gives you a lot of very useful functions which can do a lot of these steps for you. So virtually every step in this process which you require for any sort of machine learning task like this. So things like one hot encoding categorical fields, there's a function to do that. Tokening text fields and removing common stop words. And then performing that n-gram analysis where you can consider adjacent words as one token to train your machine learning network on. And then vectorizing the tokens to split out your text fields into a bunch of different categorical variables, essentially. And then producing one nice, tidy, clean vector, which you're going to use as your machine learning input. So these are some of the tools which you have available to you. So it's a really easy, clean API that gives you things like your string indexer, one hot encoder, tokenizer, n-gram, count vectorizer, vector assembler, and stopword remover. And it gives you a very nice, straightforward ability to define what your input labels are going to be. So we don't want to define our input column as our FOL. So that is our FOL link. And we want to transform it into a label column. And all you need to do is say which columns you want to convert into feature and label columns and throw it into a pipeline. And it will build out that very repeatable process that allows you to fit a pipeline to your training data and perform the comparable transformation on your unclassified and test data as well. And if there are questions about some of the more specific ways that I implemented this, we can certainly address those at the end. But I just want to make sure that we can keep moving at this point. So this is that pipeline where you can take all of your individual little components and put it into a pipeline so that the actual process of transforming the data is as simple as just calling the fitted pipe function onto those data sets. So these are the actual PiSpark data frames here, and it's as simple as that to transform them. So what we have coming out of that process is where initially we just have a product ID with a categorical vendor name and a product description. We now have two funky looking arrays which don't seem to immediately bear the resemblance to the binary matrix which we were trying to get to. So this is what we imagined we were going to get coming out of machine learning transformation and data prep step. And what we actually have is this funky looking thing where instead of zeros, it looks like we just have a bunch of ones and some very large numbers. So what this is the PiSpark sparse vector, and its function is to serve as a very memory efficient way of encoding the exact same information that you would have in a vector, so a one-dimensional array that is sparse. And by sparse, what we mean is that it contains very little information relative to the size of it. So obviously, if we're encoding vendor, and we have 9,400 different vendors, which we're considering for our train set, then in our one hot encoding process, we've added 9,400 different columns onto our machine learning matrix, which obviously, because each product only has one vendor class, every single product for its vendor encoding has 9,428 blank columns. So 9,400 zeros and one one. So your data is almost entirely blank. And so we can capture the exact same information just by recording where that non-zero value is. So all this is saying is that for this product, for all of the vendor columns, all 9,400 of them, every single one of them is blank apart from column 90. And similarly, for this product, every single column on the vendor encoding is blank apart from column 577. And a similar approach is taken with the features. So this is the exact same type of construct, but obviously we can have multiple features. And so what this says for this product, for example, is that there are 109,000 different features which we're considering for purposes of our machine learning analysis. And every single one of them is blank apart from the features with these indices here. So you can imagine that for a very large data set, this can save you an awful lot of memory in terms of keeping all of that same information encoded. So this is just to give you a recap of that. So this contains the exact same information that is given in the features of this binary matrix, but it's a lot smaller. So we've gone from 30 data points down to 11. And if you have a very big data set, you can end up saving, almost 100% of your memory just by encoding it more efficiently. And that is what PiSpark does as a default. So having got the data to a point where we can start thinking about doing some machine learning with it, the obvious next question is, okay, well, what type of machine learning are we going to want to use? The most obvious approach would be to say, okay, well, we've done all of this pre-processing in PiSpark. Can we just use some of the machine learning tools which are available in PiSpark ML to, build a neural net or a logistic regression or whatever it is that we want to do with our data that's going to produce a predictive model on those target variables? The challenge that you run into when you have parallelized data, as in the case of a PiSpark data frame, is that sadly, while you're doing linear tasks, such as transforming each individual row into a sparse matrix, into a sparse vector, for example, and doing things like the data cleaning, the number of workers that you have, so the number of worker nodes which you have out in your cluster can directly correlate to the speed at which you're able to accomplish a particular task. Unfortunately, it doesn't work quite the same way with machine learning, because in order to improve a machine learning model, you have to consider all of the data. And you can't, as it were, build a machine learning model on individual little parts of the data and build one machine learning model which is as good as one which you would have built if you considered all of the data simultaneously. And so what that means is that if you want to either build a model in parallel, you either need to spend almost as much time doing it or just have a worse model than if you've done it on the local version. The obvious trade-off of doing so is that you can build your model in a much more memory efficient way than if you just plowed into it with a straightforward approach. But it's just to say that there are trade-offs to doing so, and there is not necessarily a direct correlation between having a bigger cluster and getting a better. So the next best option, which most people would use to approach this type of task, would be to use a model out of the box, as it were, from a library like Keras or scikit-learn has a lot of models which can do this type of thing in terms of building out these neural nets in a very simplistic fashion, where you simply need to tell it the architecture which you would like it to build for you, and give it some data, and it'll run with it and build a model for you and give you some fantastic results. The third option is to go with a lower level API, such as TensorFlow or PyTorch or another library like that. And I should mention that as the most recent version, Keras is actually fully integrated into TensorFlow. So it's not really fair to consider them as two completely separate options anymore. But this was as of the time writing up this presentation, they were still kept separate. But when you're doing things at the lowest level in TensorFlow or a comparable library like PyTorch, instead of just having a high-level API where you essentially tell it the architecture that you would like it to build for you in terms of the net, you have to do a lot more boilerplate work yourself in terms of designing the architecture and making sure that everything is running smoothly. So what do I mean by that? Well, so I know that Dave talked a little bit about and gave an intro to what a neural net looks like. So you have an input layer and you have an output layer. And each one of these bubbles here corresponds to one of our feature variables. So for example, this is a very simple dummy neural net where there are just 4 features and only 2 classes which we're trying to predict it to. And what you're trying to do here is you take your feature variables, and you do some transformations. This is what the transformation actually would look like in this case. You would multiply it by, and this is, again, just a graphical representation. Nothing actually looks like this in the code. This is just a graphical representation of the matrix arithmetic, which is going on behind the scenes to transform this 5 by or 6 by 4 matrix here into a 6 by 2 matrix, which represents your output variables. And what you're trying to do at the very basic level is randomly initialize a bunch of weights and biases and perform these matrix transformations, which will whittle your larger feature matrix down to a smaller target matrix. And then you just do an assessment to see, okay, well, these are the probabilities which we calculated here off of the basis of pure randomness. And you do an assessment of how close those are to the actual labels in the training data to calculate a loss function. And having done that, you work out using a bunch of very clever matrix calculus how you could tweak each one of these individual weights and biases within your neural net parameters to marginally make your loss function a little bit smaller relative to the data which you are considering at that point in time. And that'll obviously improve your data a little bit, which will make your predictions maybe a little bit closer to what they should be relative to the actual labels for the training data. And you keep feeding data into your neural net and iterate through that same process over and over again until eventually you get your loss function to be as small as you possibly can. And that's the neural net training process. So what TensorFlow allows you to do is to do a lot of this stuff almost by hand. And you might very well ask yourself the question, well, why would you possibly want to do that when you can just pick up and go with a model like Keras, with a tool like Keras or scikit-learn, which can take care of a lot of this stuff for you. So to do this with scikit-learn, you could really easily say, okay, well, I want you to build a neural net with one hidden layer of 5 nodes with 4 input nodes and 2 output nodes. And it'll just do it for you. And it'll calculate all of this stuff under the surface, and you will never have to worry about any of this. I would say there's 2 very good reasons why you would want to consider doing this at least some point. The first reason I think is probably the most compelling for most people, which is that by doing this yourself, you have a very granular understanding of exactly what process is playing out when you hit run on a higher level model, which can certainly help when it comes to issues like troubleshooting down the road and understanding why your model might not be performing in quite the way that you would want it to. The other thing which really stands out for me is that by creating all of this by hand, essentially, you have a lot more control over the matrix and can have the ability to introduce a level of customization, which you would not have if you were just using an out-of-the-box solution. So I'll go into a little bit about why that's specifically useful in the example which I give you, but there are attributes that I have used in my machine learning process to do the Fawcett the web taxonomy, which you could not possibly do if you were just using an out-of-the-box solution. And okay, so let's go into a little bit of how to build some of this stuff out in TensorFlow. And so this is a diagrammatic representation of what TensorFlow can allow you to do. So here we have our input layer, and we just have some parameters, which I just described. So we have our weights and our biases. And it is as simple as multiplying matrices together, adding matrices together to get a hidden layer, and then repeating the process again with an output layer. And all you then do is compare your labels to your output function, your logits, and that's what gives you your loss function. And then you tell TensorFlow to run its optimization process, which it can do for you. So that's the big plus of using TensorFlow, is that it has those optimizers built in. So you don't have to do the actual, gradient descent optimizations or whatever it is that you would choose to do by hand, which is the real lift, which you probably wouldn't want to get into. And it'll optimize all of these weights and biases for you in an iterative process that will get your labels to be as close as possible once you run the data. So with that, I will go into my workspace and show you some of the little things that I've been playing around with. So at the most basic level, TensorFlow is a framework that allows you to define these matrices. So for example, when I call a placeholder matrix, I'm telling TensorFlow that I'm going to be putting data into this placeholder. And so the two placeholders which I want to define are going to be an input layer for the features and a label tensor as well, so that we can define, so that we can calculate those losses. And we can define our weights and biases. So here I'm saying that I want to have a weight function which has a shape equal to the size of the input layer and the output layer, so that we can so that the transformation will create a tensor right width. And I want to have a number of bias variables which are added as well. And so this is a little bit hard to read, and I apologize for that. But what we're doing here is we do linear matrix multiplication of our input layer with the weights, and then we add on the biases, and then we perform a leaky ReLU transformation. So that's what we call the activation function. And the reason to have an activation function is that it introduces a degree of non-linearity to this calculation. So if you didn't have the activation function and all you were doing was combining weights and biases together, the actual transformation between the input layer and the output be expressed as just having one layer, because all of the parameters could essentially be summed to just one set of replacement parameters. And if you only had one layer, it would mean that essentially you could only solve linear problems. And obviously the real advantage of neural nets over any other type of classifier, so for example, compared to like a logistic regression without advanced feature engineering, means that you can solve a lot more complex problems which don't have a linear decision curve. So having defined our output layer, we can then define a loss function. So this is taking a softmax cross entropy between our label tensor and our output layer. And then we can do some other functions useful for defining parameters which we can use to assess the performance of the matrix, of the neural net training process. So for example, we can calculate some probabilities and some predictions which generate the actual numbers which corresponds to the index of the target variable, and put on the actual labels and generate the accuracy and stuff like that, and define an optimizer. So I am using an Adam optimizer, so it's a little bit more complex than the gradient descent process of optimization, but works in essentially the same way, which is that iteratively we're going to feed it the loss function, and embedded in this loss function is all of the matrix transformation, which has gone from combining the input features with the weights and biases to understand how varying each one of the parameters in the weights and biases individually would result in reducing that loss function marginally. And so by running the loss function through the optimizer, we can improve our model. So just to get a little sense of exactly what we're talking about here, let's have a little look at how we call these things. So if we just define these objects, they don't actually do anything. So if I look at, for example, what is our input layer, and can I just look at the data? Well, there is it's a tensor, so there's not actually any data there, and it doesn't have a defined shape because it's been set up to accept whatever you ask for it. And similarly, if we look at the weights, we can't actually see any values there because it's just an empty tensor. So what we have to do is set up a process where we can essentially pour data into the TensorFlow model and get it to generate an output for us. So what I've done to just generate some dummy data so that we can understand the process is I've created these functions that will essentially create fake data for us. So here we have a feature matrix, as it were. So we just have 10 features and 3 target classes, which we're trying to predict into. And our objective is going to be to build a neural net, and this could be representative of any machine learning task. All we're trying to do is build a neural net that can transform this data using a bunch of matrices into this data. Makes sense. So let's take a little look at what this looks like. So here we have a very simple neural net, which has one hidden layer. So we're just doing one stage. So sorry, no hidden layers. We're just doing one stage of transformation. And TensorFlow has a really handy object, which allows us to look at exactly what this architecture looks like just by stringing these tensors together. So it's called the Tensorboard, and it interfaces very handily into Databricks, and it will allow you to really pull up extremely easily what the complex set of steps which you've encoded here actually would look like if you were to graph them out. So here we have our input layer and our labels. And so we're combining our input layer with some weights and biases to generate some logits. Our logits we can use to get probabilities and predictions. And then by comparing our labels with our logits, we're able to do a softmax entropy, which generates a loss function, which ultimately creates gradients, which is what our optimizer is able to train on. So if we run it on some of our data, so I'm just going to feed it the data. So one of the things that you always have to remember to do is that this is the shape of the tool which we've created, but it's not doing anything because it doesn't have any data. So what you need to do every time you run it is you need to put data into your labels and input layer. And then once you've filled all of the input tensors, you can pull out the results at any subsequent tensor in the process. For example, if I were to run our input layer, you can see what that would look like. So this is the data that we're pulling in. And so because our feature data, which we generated at this point, we are telling it to go into this feeds dictionary object. So we were creating a dictionary which maps a tensor to a data set. So this is a NumPy array. And because we have filled all of the tensors which we need to generate this particular output, so input layer is obviously only dependent on input layer, we can then run the TensorFlow session to generate this output. And similarly, we can now look at the weights, for example, because we are initializing them. And so these are completely random weights, which we've told them to just initialize themselves with a truncated normal function. So there's nothing to these weights. They are completely random, and the same as with the biases. And we can now see what our output layer would look like as well. So these are 3 classes which we're trying to predict into. And as we can see, this isn't really telling us anything useful. So what we need to do is run our optimizer successively so that we can generate a better output layer. So if I was to, for example, look at what the accuracy of this current process is, its accuracy is 0.3, which is a third, which is what you'd expect to randomly get when you have 3 classes. So what we need to do is run our optimizer 100,000 times. Let's run a little bit less than that, take a while, and then see what the accuracy is after this process. So now we can up the accuracy to 44%, or we could run it longer. And get even better accuracy. Again, this is random data, so we're not expecting necessarily a particular result. Let's also play around with what happens if we build out some tools to just record the functions, record the performance of a bunch of different configurations of neural nets. So first, let's try just recording the accuracy over the iterations that we're running for a single layer neural net with an Adam optimizer. And I should also mention what we're doing here is we're doing a batched approach as well. So we're not just going to feed all of the data in at once. We're going to feed in just little chunks of the data and optimize on each little chunk. That has some, there are very good reasons for doing so. Firstly, it saves you a lot of memory because you're not optimizing on your entire data set with each step. And it also means that you are, in a sense, randomizing the data, which means that you're going to improve the generalization of the model. And because you're not assuming that your unclassified or test data looks exactly like your training data. So here you can see what it looks like if we ran this model for 100,000 iterations or 50,000 iterations, we would get to a point where we only have 48% accuracy. So what I've done for this second model is I've built a model which has one hidden layer. So I've created 2 sets of weights and biases. And I've now got this hidden layer where I do the same. So it's a matrix multiplication between the input layer and the weights with the biases added on, and then a leaky value activation function. And that's repeated again for the output layer. So what our neural net looks like is this. And in terms of all of the supporting other tensors which go in there to perform all of the actual optimization steps, you can see that it's quite a lot more complicated. So we can run that and it should give us significantly better results. And we can see that straight away we're getting an accuracy that's significantly higher than the point at which the single layer, the zero hidden layer neural net was able to achieve, which was around 50. We're shooting right past that and going, well over 60. And so what I did was I copied this out a bunch of times and tried training neural nets with different numbers of layers. And so you can see the results of those plotted with accuracy against the number of training iterations. So you can see I ran each one of the models with a single layer batched Adam, 2 layer, so that's 1 hidden layer, 2 hidden layers, and 4 hidden layers as well, over 50,000 iterations, and plotted the accuracy over time. So what we can see by doing this is that actually the more hidden layers we used in this model, the faster the model was able to converge on very high accuracy. And without using any single layers, which is what would happen if you didn't include an activation function, or if you didn't include enough hidden layers full stop, you cap out at a very low accuracy because the model isn't able to conform to the more complex feature shape. So that's why you get better performance with more hidden layers, because they're able to more quickly converge on a more complex shape, which you need to fully fit the data. So that's probably enough of that for now. So let's go back to the presentation and talk about the actual implementation and how I made this into a useful tool. Took some of the very technical stuff and made it into a useful tool for the business in order to help provide value to their process. So this is just to talk about the process of training the neural net. So and the terminology. So an epoch is one run through the data, and in doing that, you split the data up into a number of batches randomly, so that you can train the model on one little batch at a time, which, as I say, is more memory efficient, and also randomizes the model so that it doesn't get stuck in local minima of the function. So this is obviously, I didn't have this big random system where I was copying out weights and biases the whole time. I defined a bunch of functions that would automatically build these layers out for me. So this is a dense layer function which I wrote, which would take an input layer and automatically generate an output layer based on whatever number of hidden nodes I want to do, and wrapped it all up in a function which would build a model for me based on just having just by telling it what the architecture was. So essentially what I built for myself was an API that was similar to Keras. So I now have a tool where I can just say, okay, I want to build an ensemble model which consists of 3 different neural nets, which have 1,000, have 1, 2, and 3 hidden layers of 1,000, 2 of 1,000, and 2,000, 1,400, and 1,200 hidden nodes each. And the training process is as simple as just telling it to train on the training data and produce classifications on the output data. Again, you are quite entitled to ask the question of, well, why have I bothered to go to the full extent of building myself essentially my own API for Keras? Well, the reason is that going on inside this is a lot of complexity, which you're not able to build out just using standard machine learning tools. So things like working out confidence intervals to generate metrics, which are very helpful for the business when it comes to actually putting this into action. I also built a process that would enable some of the back-end processing of the machine learning process to be done using Spark, which really speeds up the training process and also makes it a lot more memory efficient than you could do if you were just to have all of the data on the driver at any one time, which I thought I was able to circumvent. But I think that's a little bit outside the scope of what we have time for, which is not a whole lot more. So I will crack on. We can revisit if you want to. And so, running this very simple snippet of code here, which is now obviously very portable, and having gone to the work of building out those very complex systems, we now have a tool that we can very quickly deploy for new applications. In a company like Ferguson, there's plenty of those, which are very similar use cases in terms of just needing to quickly get a machine learning model, which we have full control over, up and running and into production. But this is what's going on behind the scenes. So it actually builds 3 different, while we just run this code, we're actually building 3 neural nets here. And as you can see, if you look inside each one of those neural nets, this is familiar because it has all of the same underpinnings there. And just to get an idea of why this was time best spent, so it's a conventional model. It would have cost, this is what was actually pitched to us by a consulting company for this particular application. The model would require a huge amount of memory in order to run all of those processes and take best part of a full working week essentially to do the data processing. Whereas the bespoke solution that we were able to build out, because we have code, now runs in under an hour. And the cost savings and efficiency savings really speak for themselves, because we're able to use much smaller cluster than we would have to if we went with a straightforward solution. And yeah, I think, obviously without getting too much into any more into the weeds than I already have, although I'm very happy to answer some questions on that, clearly what built out works. So just to touch on how we productionize this. So as I say, everything is built in Azure, and our tool of choice is Databricks. All of our data we get from a Microsoft Azure blob storage, which is not actually where the enterprise data lives as its full-time home. It's actually in a SQL data warehouse. We've run into some limitations in connecting Databricks directly to that SQL data warehouse, because as we roll out the capabilities across the organization, we don't want everyone who has access to Databricks to have the permissions on the SQL data warehouse, which are required in order to access data directly. Just because of the risk of adverse reactions on the SQL data warehouse, which is obviously essential for a lot of business processes. So the data is moved to Microsoft Azure blob storage as an intermediary step, which is where we're able to pull data from very, very easily from Databricks without any problem whatsoever. And we then output the results from our model in terms of our predictions to a SQL database, which also resides in Azure. And this is where our business partners, so the people who are actually in charge of the data management, pull all of the results from and do what they do with it to upload those to the actual product data repositories. So this is just an example of what we're actually generating here. So these are a list of 24 examples of products which right now don't have any classification in our product database. And what we did was we took a calculation based on just the product description and the vendor ID, which I haven't got in here because it's just a number, doesn't really mean much when you're reading it, but built a process which essentially can do what you would try to do by hand, but for millions of products at a time, which is read this product description and work out, based on existing product data, which category it should go into. So you can see that clearly Ferguson has a lot of work to do to assign its capacitors and melts into our web taxonomy. So, read this. Again, like this is a situation where if I'm not a product expert, this would be very challenging for me to work out which one of 1900 categories we should put this into. But the machine learning tool has clearly seen that there are enough other products which have microfarads and maybe 330 volts in the product description, that it is extremely confident that this product should be put into the capacitance route so that it can now be sold on our website as a capacitor. A little note about the confidence interval. So this is a tool, this is a metric that we built out, and so doing so was one of, the ability to do so was one of the primary reasons that we initially started to use TensorFlow, because we wanted to integrate it into the process. It is a metric that enables our business units to know very quickly whether they should have a high degree of confidence that the first prediction is likely to be correct based on how well the model was able to train, or if it's a very low quality prediction, which obviously can happen because sometimes we have new product groups or new vendors or products that just have bad data. We want to be able to flag out the difference to our product users so that they can make that distinction. So what that means is that when they have a high confidence assigned to them, that means that they can really just throw these straight into the database and treat these as almost 100% correct and really do very minimal validation. Whereas if the confidence output metric is low, then we obviously encourage them to spend a lot more time validating the results there, and we'll work with them to build additional tools that will help them see the process. But this is quite a critical part of the tool, because ultimately our aim here is to build a method that's going to allow the business to classify products a lot faster. And if all we can provide them is a list of predictions, which are obviously going to contain some correct predictions and some incorrect predictions, because that's the nature of the beast when it comes to machine learning, and we are not able to help them in any way distinguish between the good predictions and the bad predictions, then we may not have actually done that much to help them, because they might have spent almost as much time sorting through the results to try and separate the wheat from the chaff in terms of the output of the machine learning process. So this is an example of how in this type of work, it's very important to stay focused on exactly what you need to provide to the business to provide the maximum value. And just to give you a little bit about how we calculated this, so we would calculate the ratio between some of the predictions which the machine learning tool was creating. So, for example, just take the top two predictions and generated a probability ratio between those predictions. And obviously what that means is that if a machine learning model is very confident in a prediction, it's very likely to put almost 100% probability on one particular outcome. Whereas if it is less confident, then that probability might be more dispersed over a larger range of target classes. And by ranking all of our products by this ratio of probabilities, and then looking to see at what point the cumulative accuracy from the highest probability ratio to the lowest probability ratio, the accuracy falls below 99% based on the test ratio. We're then able to project that onto the unclassified ratio and give onto the unclassified data, and give our best guess as to whether we think the probability of a particular prediction being correct is above or below 99%. And that is what enables the business to work more quickly with our results. Okay, that's pretty much everything that I had planned to say. So I know that I jumped around and went quite quickly there, so I'm very happy to just open up the floor and have a discussion if anyone has any questions. But thanks for listening, and yeah, been great.
Thanks, Tom, for this insightful session. So we do have one question from the attendee, and the question is, did you use any visualization tools such as Tableau?
So as a company, we are tied into everything we work is with Microsoft. So we use Power BI as our data visualization tool. We didn't opt with going for using Power BI in the output in any stage. So what we delivered to the business in this particular case was just to say, okay, we have this database which you're going to have access to, and you can tap into that and pull these results out. We have used Power BI for a lot of our other projects, which we've worked with other business teams on. The main limitation that we had with using Power BI as a potential front end for this is there are limits both in data size and in complexity of how much data you can export from Power BI, I believe. And that wasn't a problem that we wanted to run into in terms of there being millions of products which we had created an assignment for, and that to be a bottleneck in the process because they couldn't pull them all out of Power BI at the cadence which they needed to.
Okay. The next question is, are there any best practices for determining initial number of hidden layers? And then how do you decide to add or remove layers to your model?
Yeah, so this is a really important point. And, in the literature, it says quite a lot that I have read that there is no theoretical reason for having any more than 2 hidden layers in a neural net. I think just from my experience, that doesn't really bear out in reality because, for example, for particular problems, you may well find that even if you can't generate a better model using more than 2 hidden layers, you may generate one which trains significantly faster because there are more degrees of freedom, which means that it can coalesce onto a working model better than if you had a simpler tool. I think also having more hidden layers gives the model more flexibility, and you're not likely to get sucked into a local minimum. I think really the best rule of thumb for any of this is to understand that there are no hard and fast rules when it comes to architecture, particularly when you're looking at very diverse problems. And one of the best approaches, which I found has been very impactful in terms of building out tools which perform well and generalize well to unseen data, is ensuring that you have multiple different approaches. So using an ensemble approach where you can have more than one model, and they may even be different types of models. So obviously for this particular situation where we're doing this multi-class approach, you're not going to be using anything like a linear regression, but you might want to use things like a random forest, which could solve this type of problem as well. And so you may want to combine different types of model, and then your ultimate predictions are based on a combination of the predictions of the various different types of model. But there's no hard and fast rule for what you would want to set as your optimum size of model. It's really a trade-off in terms of, because you're unlikely to get a less effective model because you've added more hidden layers or more hidden nodes. What you're likely to see is that you may just have a model which is very heavy because you're carrying a lot of parameters. So your training time may be longer, just to optimize each step. And you may find that it also is very memory intensive on your system. What I have found, one thing which I have concluded from my research on this is that I can actually get away with having an extraordinarily low number of hidden layers, hidden nodes. For example, I can have a problem where my output has 1900 nodes, but I can actually have a hidden layer which has only 1000 nodes, and the model can still perform as well as one which has a much higher number of layers and nodes. And the reason for that is the sparsity of the data. So because there are only quite a finite number of combinations of features which actually appear commonly together, the model can actually create the necessary pathways through the neural net with actually a surprisingly small number. So all that to say that it is very contingent on the specific problem that you're facing, and it's always advisable to just experiment until you find what works best in your particular application.
If you have any follow-up question, feel free to unmute yourself and ask, or you can just type them in chat window as well.
So I'm happy to talk about, I know we only have 6 minutes left here, but I'm happy to talk about any other aspect of this model or other models which we've built at Ferguson, or if anyone has any other feedback or thoughts on the model, I'm very would love to hear that as well.
All right, looks like we're good. Tom.
Awesome. Well, thank you very much, everyone.
Thank you.
It's been a pleasure. And I think you can find my contact details through the session eyes, I believe, if anyone has any other questions which they would like to follow up offline.
Thank you very much, Tom. We really appreciate that. And then our next speaker is Ron. Looks like Ron is online. So Ron, can you quickly unmute yourself so we can quickly do audio and screen share test?
Hello, this is Ron.
Hey Ron, we can see you fine.
Package ready.
And we can hear you fine as well.
Yep. Let me see how I can share my screen. I can share my desktop screen. Here we go. You see my screen now?
Yes, looks like we're all set. So thanks. And we can start right at 2 p.m. Eastern time. So that will give some other folks to jump between other sessions. And thank you very much for speaking, Ron.
Oh, you're welcome. Anybody, everyone having good time or any good sessions that you've attended today? Feel free to place them in the chat. And I have, the last few sessions I've attended in the ML is very interesting.